So hello everyone and welcome back. In this session I will show you how to compile the code in both serial and parallel modes. But before we go to the terminal, I would like to point out to a couple of things here. And the first thing is that the code is not pre-compiled, fair enough, meaning that you have to compile the code before usage and after you clone it from GitHub. But at the same time, whenever you make any change to the source code, you have to recompile the code or recompile these functions. And automatically the tool make will identify what type of files or what files were changed, and then it will compile them alone without recompiling the whole code. And the second thing is that the code is a single executable, meaning that we have one numerical solver with different settings, and every time you solve a problem you have to adapt the code to this specific case, or you have to tailor the code according to your needs through the control files or the input files that we call them control files in this code. And you will see this in a couple of sessions and you will master it, no problem. And for the third and fourth point here, those are the user mode functions in the test directory, which is the benchmark cases. This we will see together in the terminal because it makes more sense to explain it there. So yeah, let's go ahead and go to the terminal right away so we can practice together. Alright, so let's say this is your working directory. Go inside tflows, and the first thing you need to do before compiling the code is to know on which branch you are. So in order to know on which branch we are now, you type git branch -a, and then it will list all the branches that are available in the code for you. And what you need to work on, which was created specifically for this course, is this branch, Mohammed tflows crash course, TFCC. So you need to check out to this branch, and checking out to a branch meaning that we're switching or we're going to that branch, we're moving or switching from the main branch, which is this one here, and this asterisk is signifying that we are currently on this branch, main. So we move from main to Mohammed TFCC through git checkout. Let's go. And then it says now that you switched to the branch Mohammed tflows crash course. So we're now in the right branch. Now let's go ahead, let's clear this and maybe go to the test case, or maybe before the test cases, and I show you the compilation process first. So now let's go to the process or to the sources, and then go to process, and then that's the main Navier-Stokes solver. Huh? So you have all of these modules here, and let's say, for example, we open one of them. Let's say we take matrix mode. So at the beginning of the function or of this module, you have a bit of a documentation of how the matrix is stored. And then here you have type, which is an object of matrix type. And then you have the data members. So you have a number of data members which are essentially used to store a matrix. And then at the end here you enter type, and let's say if I show the number of the lines, so on line number 57 here you have include matrix, so which is here you're including or calling a function that creates a matrix. So that's basically the structure of an object-oriented program, or this is what resembles the object-oriented program. That you have a number of data members here, and then you have a function that operates on these data members. So this function is basically using create matrix, is using these data members to create a matrix and store values inside them. So yeah, that's how the code is built in pretty much all of the modules. So now let's go to sources to build the code together. And just to recap quickly, we have the main programs that constitute tflows, which is process, convert, divide, and generate. And let's start off by building process. And now what we need to do to compile the code is just to type make. And if we want to compile the code in serial, this is all what we need. We just type make, and make will compile the code automatically. We'll build all of these modules that I will show you in a minute. or maybe while it compiles, I can show you in a different directory, in a different tab. What we have this in this file is the main code is here. Main Pro is the main program that has all the modules that TFlows has, and it includes all of them, as you can see here. And so TFlows is actually built in a highly modular way. It's not really object oriented in terms of how it would be in C++, for example, but it's still highly modular in a way that it mimics the object orientation in a way that every module of those, let's say turb mod is the turbulence module, swarm mode is the Lagrangian particle tracking module, and VOF is the multi-phase flow, so the solver type, and then turb plane type or monitor type. All of these are modules that contain data members, and we have at the end a function that operates on this data. So now if we go back, the code is compiled already, and this is the main compilation process, which is process. And what we need to do now is to go to divide, for example, and also compile, which is the main decomposer of the code. It decomposes the domain into subdomains. In case we want to run in parallel, we need this one. And after it compiles, if you really use divide, then it means that you're running in parallel. And if you run in parallel, you have to compile the code in a slightly different way, which is you go to process. It's basically the same way that you have to clean first. You have to make clean. Let's do it step by step. So make clean. We cleaned already the compiled files. And now instead of make only, you say make and MPI equals yes. And in this way, you compile the code in parallel mode. So you can prepare it actually to use MPI, which is the message passing interface algorithms that will prepare the code to predict or wait or kind of expect you to provide subdomains, and then it will start communications between these subdomains and interacts between them in order to compute your problem faster. Now after you compile this one, we can go ahead and compile generate, or you can actually do it also at the same time in another tab. Then you can do generate. Inside generate you can make. Executing make inside each of these programs will just compile the tool for you. And you can see already that we're compiling two tools at the same time. That's no problem. And inside this guy, maybe we can go to divide, list, and make. We made already. We compiled divide already, and I forgot. What we just need is convert. And convert, as we mentioned before, is the one responsible for converting the external meshes into the local format of TFlows. So we use it only when we have an external mesh and we want to run this or operate this mesh inside TFlows and run the TFlow solver on this mesh. So we use convert first to have it on our side, and TFlows can read the mesh and interacts with it. Then you run process to solve the problem. Now we have all compiled, and if you want to check that, if you want to make sure that you compiled all the programs, or what you want to check, let's say, which programs have you compiled successfully already, you can list the binaries directory, which we talked about before, and the binary files should contain all the executables. So if you list them, you can see already we have convert, divide, generate, and process. So we have now all the executables ready for us. Now one last thing here I told you about at the beginning of the session, that I will tell you about this user mod functions. So those are user modified functions. You can interact with the code or manipulate the solution in a way, or let's say you have a good interface without changing the source code with what's happening in your problem through these user mod functions. And they're actually built also in a modular way and very easy and straightforward to understand. If you go inside this guy, you realize that you have a bunch of functions that are fairly simple and straightforward. Each of them is empty, is an empty function. You can see that those are just templates, huh? If you go inside this file now, you will find out that you have a list of functions, and each of these functions are is a template. So if you, for example, open this, let's say beginning of compute momentum, then you open this, and if you go inside user mod, you realize that there is a list of files or list of functions, and each of these functions is just a template. So it's basically, let's say you open the beginning of compute momentum, let's choose this one. You can find pretty much that it has nothing, huh? So it has only these aliases, but it's an empty function. It doesn't do anything. And what is this used for? It's just used as a hook, or as you will see in a couple of sessions. This is not necessarily that you will need to use, but just in case that you wanted to interact with the code, or you wanted to do something at the beginning of the momentum solve, you interact with this one here instead of changing the source code, and you maybe mess up something on your side. So it's a very elegant way to use this. It's just to have some of these functions, or whatever you want to have, you pick it from here as a template, copy it, or link it to your test case. And once you have it in your test case, you can link that. You can link the solver to your test case, and it will pick up already this hook. So every time you compile the code, you will find out that the user mod functions are hooked. In this case, we didn't really link process while compiling the code to user mod, to any test case. So there is no linking. So if you list here, there is no links that you can see. But in a couple of sessions, you will see already that when we compile the code, let's say if you do make and MPIES, and then in the future we will use a tool like this, which says directory case, and then let's say you show, and then let's say you go to one of the cases that you want to solve, let's say membrane 2D, something like this. And if you compile the code in this way, then any user mod function, you can see already that this side, you can see already that this test case, for example, contains a user mod function, huh? So it contains a user mod function. Once you compile the code in this way, with this line, so you're basically just adding one path to directory case, and this path means that for TFlows, that when processes compile, it has to link to any user mod function existing inside this directory. So it's not only compiling, but it compiles and links to any of these user mod functions that may exist in your test cases. Otherwise, if you don't have any, and if you don't want to use any of these user mod functions, you just compile the code in the way we did, like this. So you just make an MPIES. That's in case of a parallel mode, and in case of serial mode you run with make only. So that's pretty much it. The last note that I wanted to mention here is that the default settings in the tests directory, there is an S missing here, should be always checked before use. So let's say you have a bunch of parameters for the flow and physical properties and turbulence modeling and stuff like this, as we will see later in the course. Always make sure that you test or you check or double check the parameters existing in this test directory before using it, and please don't use it blindly. Otherwise, maybe you run into a case that, let's say, injects lots of particles, or it has many time steps, and then you end up with your PC occupied for a long time if you don't know how to kill the process. So just in any case, to be safe, always check these files, check these input files before you run the case. Otherwise, maybe you kind of expect results and then you run into a problem that you have results for something else. So yeah, that's it for this session. Thank you very much for watching and see you next time. Bye.